Okay, so my day job, I'm a faculty at the University of Wisconsin, but today I want to talk to you about some technology we have developed at the University of Wisconsin over the last 10 years, and we finally think it's ready for prime time, so to speak. The technology name is Scan and Solve, and the best way I could summarize it is that I would call it finite element analysis without meshing. And I want to emphasize that not without mesh, but without meshing. Okay? So this is, in few words, how it's supposed to work. So what you see here on the first picture, all the way to the left, is a geometric model. The holes are supposed to be fixed, and some forces can apply to the face. And so we're solving structural analysis problems. The first step is what we call scan. Normally, when you think of scan, when I think of scan, it's a process of determining the distance to a boundary of a known object. So the same way here, you can think of computing the distance to the boundaries of known objects, which are red holes in this case. Holes are where the boundary conditions are. The result of that process is what you can think of a function, a field, which for every point in space knows that distance to the red holes. It doesn't know anything about the solid, but you can plot it over the solid, and you get this other picture on the right. So that's kind of the end result of the scan process. Now what? Now we want to solve the analysis problem. Of course, we need to solve it with something, so we bring our old friends, shape functions on some mesh. In this particular case, that's the mesh. That's a mesh of space. It's not mesh of geometry. It's a mesh of uniform mesh of B-splines functions. So B-splines are sitting at every node, but it could be your regular non-conforming mesh of finite element analysis, or it could be some collection of radial basis functions floating at points, or whatever you want. They don't know anything about geometry. They don't know anything about boundary conditions. But at runtime, all of the things are going to get married. So the distance function is going to get married with the basis functions to create a new basis which knows about the boundary conditions and have enough degrees of freedom to solve the analysis problem. These functions at runtime are going to be differentiated and integrated over the original solid model because it's perfectly adequate for integrating. Okay? And then you construct a system of linear equation and you solve it. So that's basically the essence of very simplified, very fast, of course, explanation of the method. You want to solve something that other people cannot solve. So we found something that other people cannot solve. We did analysis of David by taking the original model from Stanford, which was scanned, and you can see it's a fairly messy model. And you can see the red spots correspond with the cracks. And this is an analysis that was done before us on ANSYS. So really, the people who've done analysis before should get all the credit. But they didn't get any credit because that's a crappy-looking picture. We got all the credit, and we got all the headlines, a lot of headlines, almost embarrassing headlines. My favorite is there on the bottom, which says Michelangelo is losing his marble. It was very embarrassing, but then an interesting thing happened. I started getting a phone call. I got a phone call from dentists who wanted to know if we can do analysis on crowns. I got a call from somebody from Chile who wanted to do analysis on iceberg. Horse industry contacted me. Paul Getty Museum contacted me because they want to know if we can predict what's going to happen to their sculptures when the earthquake hits, and so on and so forth. And I said, what's going on? Can they do that before? And the answer is no. It's not economic, it's not possible, and they don't want to know about stresses, they don't want to know about displacements, they don't want to know about mesh. They just want to know whether it's going to break. Okay? So putting all of that hype aside, this is what we have, all analysis of finite element analysis, but without meshing. You can do it for any finite element analysis problem, really. And if your geometric representation is good enough to compute geometry, then it's good enough to do physics problem. I don't have time to talk about theory and experimental validation, but it all works. I'm going to skip to the bottom because I'm running out of time. So deterministic, there is no heuristic. It always terminates. You can predict how long it's going to take, and if you double the resolution, it's going to take twice as fast, twice as long. Okay? No denoising, no repair. Let me just flash through some examples in the few seconds that I have left. If you like to do embossing, your mesh should not depend on the size of the letter in it. It would in most problems. This part was imported from another system. All the red things on the green, these are all your geometry problems, and most measures will fail, but just works. And complex topology, it really doesn't matter. It just works. So We call it automated analysis in situ because we want to work with the original geometry. It really changes economics and opens up all kinds of opportunities. Really integration of design and analysis because you always work on the same model. Okay, there is no conversion that's supposed to simplify and convert model and so on and so forth. You can do it on any stage in design. You can talk about parametric models that knows about their physics. I did not talk about implementation, but if you look at what is actually happening in the solution process, and I'll give you the reference, it's embarrassingly simple. There is just sampling left and a solution of linear system of equation. It is, I predict in a few years we'll be doing it in real time. And above all, and I'm grateful to Mike Payne for bringing me to realization, is that we finally can move to the question whether it's going to break as opposed to what the stresses and what displacements are. And so with that, I conclude. There is a website. You can get a lot more information and examples. And I want to thank National Science Foundation, who supported this work for over 10 years. Thank you.